Okay, so continuing discussion of time-stepping methods for ODEs and systems of ODEs. So far, the only kinds of methods we've seen are one-step methods, methods that, when time-stepping from time tn to tn plus 1, use information about the solution and evaluations of f only within that interval. Today we're going to look at multi-step methods that go further back in time. So um, so why is that an important consideration? Methods during each time step, the function f of ty in the differential equation that we're solving, y prime equals f of ty, requires several evaluations um, in order to get and we saw an example of that. To achieve fourth order, f is evaluated 4 times per time step. But it's not necessary to do this. So we can achieve high order accuracy. And to refresh your memory, okay, what I mean by high order accuracy, the error is on the order of h to the h to the p, or for example, or h to the fourth for RK4. But we could do this. We're still actually evaluating f, only one new evaluation of f per time step. So what we're doing is we're going to be using information about the solution from further back in time, and evaluations of f from further back in time in particular, to get higher accuracy more efficiently. So um, so what is a multi-step method? So we're going to use general framework. Okay. So what we have is all multi-step methods can be written in this form. And in case you look at other textbooks, what I found is that different books present multi-step methods in different ways that are all mathematically equivalent, but sometimes differences in notation can lead to confusion. I've basically gone with what a majority of books I've looked at use in deciding on my notation. Okay. So all multi-step methods can be written in this form for certain choices of coefficients, alpha I and beta I. Important. So we can classify multi-step methods as 2-step, 3-step, etc. Technically, Eulers Method, forward or backward, can be classified as one-step methods by choosing 2 non-zero values of alpha and only 1 non-zero value of beta, and n would be equal to 1. Um, so this is like a trivial example. So the number m is the uh, number of steps in the method, and then we have the maximum possible evaluations of f would be n plus 1. Now, I'm going to introduce a shorthand here. I'm going to define fk to be equal to f of tk yk. Notice the index on t and y is always the same. So this is a contrast of one-step methods that we've seen, where we have different possible expressions for t and y. For example, it might be tn plus h over 2, and then who knows what's added on to yn. But here, t and y go in lockstep. So I'm going to use this notation throughout as an abbreviation. But the thing is, even though there are n plus 1 possible evaluations of f in this method, um, that all of these evaluations, except one of them, would have been carried out during a prior time step. So there's only one new evaluation per step. So I'll give some pros and cons here. So the main advantage of multistep methods is only evaluation per time step. And the drawback is that, for example, suppose a method is a three-step method. So it relies on the information about the solution from time tn, tn minus 1, and tn minus 2. So now let's suppose you're at time 0 and you're trying to get to time 1. So n would be equal to 0 in this case. So you need the information about the solution about at time t sub minus 1 and t sub minus 2. You don't have that, and there's no reasonable way to get it. So you cannot use immediately. Must use a one-step method for the first m minus 1 time steps to get what are called starting values. So for example, for m equals 3, use one-step method to get y1 and y2. Then what happens is, because it's a three-step method, it relies on the solution information about the solution from time 2, time 1, time 0. So when you're trying to get y3, you have y0 from the initial condition, and y1 and y2, and then you can use the multistep method and continue using it from that point on. But multistep method relies on a one-step method as a kickstarter, basically. Okay. Now, we've seen with one-step methods that they could be either implicit or explicit. Sorry, one thing I want to deal with right here. I'm just going to close down my browser real quick because... Okay, once again, technical difficulties. Apparently, every single time the recording gets interrupted at least once, hopefully only once. Okay, so a multi-step method is... now, with one-step methods, we saw methods that were both implicit and explicit. For example, forward Euler, some of the Runge-Kutta methods we saw, like RK4, explicit methods. Backward Euler is an implicit method. You must solve for yn plus 1. We also saw the implicit trapezoidal method that is implicit. So a multi-step method is explicit if this coefficient beta naught, so I equals 0 if beta naught beta naught equals 0, and it's otherwise it's implicit. Because if we have a non-zero beta naught here, then we're evaluating f at tn plus 1 minus 0. So we have tn plus 1 and yn plus 1. So yn plus 1 is occurring on both sides of the equation. Therefore, it's necessary to solve for it. So to compute yn plus 1, in this case, okay, this is getting pretty aggravating, and it closed down yet again. So to get yn plus 1 in an implicit method, what you could do is use a root finding method, like the ones we've seen. like Newton's or secant, to find a root of, well, weird spacing there, find a root of this function, f of capital F of y, which is just equal to this method, set equal to everything on one side, set equal to 0. But I'm going to write terms separately. So y, just y by itself corresponds to yn plus 1 in here, because that's what we're solving for. And then we have all the other terms for previous values of y. But notice I start to sum at I equals 1 here. And we have minus h beta naught y, and then this sum again, beta I f n plus 1 minus I, using the shorthand that I described earlier. So we can use any of these root finding methods on this function to solve for y. And this function is set equal to 0. Now the thing is, suppose you use Newton's method. Newton's method requires a derivative, so you would need df dy to make this work, and that possibly might not be convenient. So if you don't want to do that, you can always use the secant method instead. Okay. Now, there's different classes of multi-step methods. Now, not all multi-step methods necessarily fall into these classes, but I think it's safe to say that most do. So if we take the ODE, and we integrate it from time tn to time tn plus 1, so we get this, and we've seen this relationship before. Ytn plus 1 equals ytn plus the integral from tn to tn plus 1 of f of s y of s ds. Now this y of t, recall that that's the exact solution. So an Adams method is a type of multi-step method, is based on approximating this integral using a quadrature rule. The quadrature rules were covered in 460, 560, but I'll give you the next necessary pieces to describe Adams methods. So the idea is the function f of s, y of s is fit with a polynomial okay. And it's an interpolating polynomial. So the idea is it passes through the values of f at various points. So the interpolation points that we use are n plus 1 minus m. So going from time longest to go to present, tn plus 1 minus m minus 1, so n plus 2 minus m, and so forth, all the way up to tn minus 1, tn. So we use whatever points, whatever time values are used in the multi-step method, and also we include tn plus 1 if we want the method to be implicit. So we use a total of m interpolation points from these, and possibly one more. Okay. So the idea is in all. Okay, some space here. So one thing that can be used to identify Adams methods, in all Adams methods, we have alpha 0 is equal to 1, alpha 1, which is a coefficient of yn, is equal to minus 1, and all other alphas, sorry, that should be alpha sub 1, not minus 1. So if there are any other alphas in the method, so it's a true multi-step method, like alpha 2, alpha 3, etc., those are going to be equal to 0. So there are only 2 alpha values. So it really determines, in particular, Adams method, are the betas, and those come from setting up the interpolation polynomial and substituting in here, and basically integrating that to approximate this integral. Okay. Now, some terminology. So explicit Adams methods. So again, beta naught is equal to 0. So Tn plus 1 is not included among the interpolation points. So those are called Adams-Bashforth. So implicit Adams-Bashforth, implicit Adams methods, where the beta naught is non-zero, are called Adams-Moulton methods. And collectively we just call them all Adams methods. And I believe it was Adams and Bashforth who developed the first version of Adams methods that were explicit, and I believe it was Moulton who came along later and used the idea behind Adams method to Adams-Bashforth methods, modified that to get Adams-Moulton methods. Okay. Now, what I'm going to do is, first let me get to a new page. Okay. So I'm going to show an Adams method, in particular an Adams-Bashforth method, but a similar idea can be used for the, and we'll set m equal to 3. So the method's going to have this form: yn plus 1 is equal to yn plus, and we're going to have h times beta 1 fn. So there's no beta naught because it's an explicit method. Beta 2 fn minus 1 plus beta 3 fn minus 2. So a 3-step method goes all the way back to time tn minus 2. So to derive the Adams-Bashforth method, we need to find the values of beta 1, beta 2, and beta 3. So to do that, we're interpolating at 3 points. So we let P2 of t be an interpolating polynomial, and it fits f of t, y of t at tn, tn minus 1, tn minus 2. I'm going to keep restarting it as many times as it takes, dang it. So we're fitting f of t, y of t at these 3 points. If this were an implicit method, we'd also be including tn plus 1. So because there are 3 points, it's a quadratic, because a quadratic is always, the degree is always the number of interpolation points minus 1, so that's why I call it P2 of t. So we express this in Lagrange form is, okay, P2 of t is equal to a sum, and we have fn minus I, because we have fn, n minus 1, and n minus 2, times, look for Lagrange polynomial, So each Lagrange polynomial is equal to 0 at all of these points, except at one of them where it's equal to 1. So then basically we're selecting the right f value here. So, excuse me. So, sorry about that. So what I'm going to do is, all right. So we look at the integral that we're trying to approximate. Okay, so what we have now is the integral Tn plus 1 of f s y s ds. The integral we're trying to approximate, that came from right here, is approximately, there's a typo in the book, it's supposed to be approximately equal to, not exactly equal to, of p2 of s ds. And what I'm going to do is make a change of variable, like a u substitution for the integral. Okay, and what is the substitution? So u is equal to Tn plus 1 minus s all over h. Okay, it's really frustrated right now. So the point of this change of variables, it maps the interval Tn to Tn plus 1 to the interval of 0, 1. And we have du is equal to minus 1 over h ds. So that's what leads to the factor of h sitting right here. So if we plug in t equal to tn, we get 1. And if we get s equal to tn, we get 1. S equal to tn plus 1, we get 0. So really, it's these limits are mapped to 1 then 0, but we flip them, and that gets rid of a minus. But this change of variable here leads to a factor of h sitting right here. And the reason why we do this is the interpolation points that we have. So Tn all the way down. So really Tn minus 1, Tn minus 2 are mapped to 1, 2, and 3. 1, 2, and 3. So it makes it a lot less tedious to work with these Lagrange interpolating polynomials. So now we have, for approximate integral, keep in mind if we want to write it in Lagrange form, p2 of u du, that is equal to, so all I'm going to do here is fill in fn, fn minus 1, fn minus 2, and each one of these f values is multiplied by the appropriate Lagrange polynomial. And putting tildes on top of them to reflect that we're dealing with the change of variable. Okay. Okay. Now, I need to make this a multi-line equation here. Okay, so with Lagrange interpolation, this first Lagrange polynomial is equal to, it corresponds to the interpolation point 1. So it's equal to 0 at 2 and 3, and it's equal to 1 at 1. So the polynomial that does that, since it's equal to 0 at 2 and 3, it has those as factors. And then we plug in u equal 1. We want it to be equal to 1, and this will certainly not be. So we divide by what we would get if we plugged u equal 1 into the numerator. So this has a desired effect, being equal to 0 at 2 and 3 and equal to 1 at 1. And same thing for the other points. All right, so this second polynomial is equal to 0 at 1 and 3. So we put those in the numerator, u minus 1, u minus 3, and then equal to 1 when u is equal to 2. And finally, the third polynomial is equal to 0 at 1 and 2, and it's equal to 1 when u is equal to 3. But now, keeping in mind that these fn, fn minus 1, fn minus 2, these are f evaluated at fixed points, tn, tn minus 1, tn minus 2, and a corresponding y values also plugged in. So they are independent of u, therefore they can be pulled out of their respective integrals. So I break this integral up into 3. Then in each one, like in this one I can pull out fn, I can pull out fn minus 1, I can pull out fn minus 2. So the only thing left inside each integral is the Lagrange polynomial. Alright, so fn minus 1 times the second Lagrange polynomial plus fn minus 2 times the third Lagrange polynomial. Okay, I need to, these are all separate integrals, so I need to fill that in here. Okay, du, then fn minus 2 integral from 0 to 1. Okay, all right. So there we have it. But now if we match this whole expression to the form of a multi-step method we were looking for in the first place, that's right here, it shows that the integrals that we have down below are equal to beta 1, beta 2, beta 3. So that's how we get them. So what we have is beta 1 is equal to the integral from 0 to 1 of the first Lagrange polynomial. And that turned out to be equal to, if we work this out, 23 over 12. Beta 1 is equal to integral over the same interval of the second Lagrange polynomial. And that turned out to be equal to minus 16 over 12. I know I can simplify that, but I want to have everything over the same denominator. That's beta 2. Beta 3 is the integral of a third Lagrange polynomial. And that turned out to be equal to 5/12. So our multi-step method, our Adams-Bashforth method, is yn plus 1 is equal to yn plus h, and we'll have 23 over 12. Actually, I'm going to pull the h over the 1/12 out. All right, so what we have is 23 23fn minus 16fn minus 1 plus 5fn minus 2. One thing I want to point out is generally in Adams methods, here we have alpha 0 equal 1 and alpha 1 equal to minus 1. It's just moved to the other side. The alphas generally always sum to 0. And these Adams methods, if we sum up the coefficients, we have 23 minus 16 is 7 plus 5 is 12. Divided by 12 is 1. So these Adams methods, the betas will always sum to 1. So it's important to check that if you're deriving one of these. That could be check, to make sure that you didn't make a mistake. All right, so that's Adams-Bashforth method, and the only change when deriving an Adams-Moulton method is for a given value of m, instead of having you'd have m plus 1 integrals betas to evaluate, so you have including beta 0. So 0, u equals 0 is included as an interpolation point. Now, what about accuracy? A m-step Adams-Bashforth method its error is order h to the m. So this is a one-step method that's like Eulers method that only has one stage. Would it be first order accurate? So here we have this three-step method. It would be third order accurate because it uses three stages altogether. And a m-step Adams-Moulton method, its error is order h m plus 1. And the reason why is there's one extra interpolation point for a given value of m compared to an Adams-Bashforth method due to the inclusion of u equals 0 among the interpolation points, thus adding an extra degree of accuracy. Dang, all I had to do was just reboot my laptop and bam, it's recording just fine. So, wish I'd given it and done that sooner. So apologize for how choppy the video is at the beginning. And no, I don't have time to go back and re-record that. Okay, so that's the idea behind deriving an Adams method and their order of accuracy. Now, one useful kind of method is a way to make implicit methods more efficient, but still try to get the benefit of their extra degree of accuracy, is a predictor corrector method. Because normally with an implicit method, as I mentioned earlier, you'd have to use an iterative method like Newton's method to get yn plus 1, and that can be fairly expensive. Well, at least you have a viable initial guess in yn. But still, that extra expense, if we can avoid that, that would be quite desirable. So a predictor corrector method uses a pair of Adams-Bashforth and Adams-Moulton methods to avoid the having to use an iterative method like Newton's method. So the procedure can be abbreviated PECE. So predict, evaluate, correct, and evaluate again. So this labels are 4 steps. Now I'm going to describe the 4 steps of a predictor corrector method. What's carried out each time step. Use a predictor, which is an Adams Bashforth, so an explicit Adams method. And this is our first approximation of yn plus 1, but it's not our final approximation, so I'm calling it tilde yn plus 1. Then what you do is evaluate. We plug this into f, and I'll call this tilde f n plus 1, which is equal to f, and we plug in tn plus 1, and normally we plug in yn plus 1. Well, this is the approximation of yn plus 1 that we have, so that's what we plug in. Okay. Then what we do is we use the corrector which is the implicit or Adams-Moulton method. And an implicit method, an Adams-Moulton method, requires, sorry, it should be f tilde n plus 1. It requires a value of fn plus 1. So we go ahead and use this. So that is plugged in. And from that, we get a yn plus 1. So that is our final value for this time step. So there's no need to iterate. We can if we want to, but I'll explain in a moment. But before we get to that, we update fn plus 1 by taking the value of yn plus 1 that we just got and plugging that into f. And that is used to set up the next time step, where this would be used as play a role of fn in the method because the index of our time step is increasing. Now, what you could do, if you wanted to, you could still iterate where I take this fn plus 1 and use it in the corrector again, like playing this role to update yn plus 1. It can keep going until it gets some kind of convergence, but it's certainly not necessary to do so. So I can go ahead and illustrate this process. All right, so we have as a predictor is a two-step Adams Bashforth. So that would be okay. Actually, going to move this onto a new page. Okay. So that method, not the same as the one I just derived. That was a free step. Yn plus h over 2, 3fn minus fn minus 1. Okay. So the idea is we use this formula to compute tilde yn plus 1. We'll have tilde fn plus 1 equal f t n plus 1 tilde y n plus 1. So that's our evaluate step. Then we correct with a two-step Adams Moulton method. Yn plus 1 is equal to yn plus h over 12. So we have 5 tilde f n plus 1. And then I have rest of the Adams Moulton method. That's going to be minus 8 fn minus f, or sorry, that is a plus 8 minus fn minus 2. Now notice this is a two-step Adams batch for two-step Adams Moulton. They, sorry, that's n minus 1. They go back the same distance in time, but because this Adams Moulton method is implicit, it also uses fn plus 1. So that approximate f value, fn plus 1, is plugged in here. So then we have ys plus 1 computed from that. And then to set up the next time step, we go ahead and compute the fn plus 1 to be used there. So that would be f of t n plus 1, yn plus 1. So that's the predictor corrector process. This is what's carried out each time step. Okay. Now, actually, I wonder if I remember recording, considering things work so smoothly since then. There's another class of multi-step methods called backward differentiation formulas. So a backward differentiation formula also known as a BDF, is an implicit multi-step method. They're all implicit, in which the only non-zero beta is beta 0. So there are no other betas. So it's kind of weird, like opposite of Adams methods. Adams methods, you have alpha 0 and alpha 1, no other alphas, and you have a bunch of betas. With BDF, you only have one non-zero beta, beta 0, which causes it to be implicit, and then you have a bunch of non-zero alphas. The alphas are obtained by approximating y prime using a backward difference. So like the simplest backward difference is evaluating approximating derivative. We're approximating y prime at tn plus 1. It's very important. Okay. So the simplest backward difference would be yn plus 1 minus yn over h. And that would actually lead to backward Euler. But generally, backward differentiation formulas use higher order finite difference formulas to get higher order accuracy. So the general form is sum I equals 0 to m alpha I y n plus 1 minus I is equal to h f n plus 1. So I said beta not equal to 1 here. Okay, actually they all can be written that way, beta not equal to 1. It's really just a normalization, but okay. And I could give you a formula for each alpha. It is equal to the Lagrange interpolating polynomial, its derivative, evaluated at tn plus 1. So each Lagrange polynomial So we're interpolating polynomial for points tn plus 1, tn, tn minus 1, etc., all the way down to t n plus 1 minus m. And this goes to, and if you look at chapter 9, which is covered last semester in 460-560 for numerical differentiation, there are two ways to obtain numerical differentiation formulas. One is the Taylor series, the other is Lagrange interpolation. So we're trying to approximate a derivative of approximate y prime at this point. So the way you obtain a finite difference formula is you take a Lagrange polynomial for the points you wish to use. These are the points that a multistep method would use. And then take the derivatives of Lagrange polynomials and you substitute t equal to tn plus 1. And that will give you the coefficients in the Lagrange form. So that's what will give you the alphas, the coefficients of a multi-step method in this case. A m-step BDF has error order h to the m. So it's interesting that m-step method BDF is order h to the m, whereas the m-step Adams method that's implicit, an Adams-Moulton method, is error order h to the m plus 1. And it's also worth mentioning that you can go as high as you want in deriving these BDFs by using more and more points. A higher value of m is stable. Now I'm put stable in quotes because I've not told you what stability is yet. That's actually the subject of the next section, which I'll get into starting on Wednesday. What it means for one-step and multi-step methods to be stable. So essentially producing a qualitatively correct solution. So we'll get into details then. So unfortunately, if you go to a too high order BDF, they're always going to be unstable from that point and therefore useless. But low order BDFs are in use. Some of them are used in the stiff ODE solvers, and stiffness is another concept I'll come to later in this chapter. In MATLAB, for example, ODE 15S, a very effective ODE solver, uses a BDF. Okay, so that's the general idea behind multi-step methods. There are multi-step methods, we'll see at least one, that is neither an Adams nor a BDF, but most do fall into these categories. So what I'll get into starting on Wednesday is convergence analysis. So how do we determine if a one-step or multi-step method converges, and we'll learn about the related concepts of consistency and stability.